Um, I'm pleased to introduce Sachin Guru-Rangan from the University of Washington. He's a PhD student there, advised by Luke Zettelmoyer and Noah Smith. He's done a bunch of influential work on annotation artifacts, wrote one of the leading papers identifying those as a problem with training data sets. Domain adaptive and task adaptive pre-training techniques, and also what he's going to talk to us about today, which is modular language models. So please welcome Sachin.
Great, thank you so much, Doug, and thank you so much everyone for having me. For those who don't know, my name is Sachin. I'm a PhD candidate at the University of Washington, and it's wonderful to be back here talking about my research with you all. AI2 really helped kickstart my career in NLP, and it's where I learned how to be a researcher as a PYI. So, you know, this organization is very dear to me, and I'm very grateful to have the opportunity to come back and tell you all what I've been up to since I left. So I'll begin with a brief introduction about the problems that we'll tackle today before digging into our main contributions. If we could keep questions to the end, that'd be great, unless you have a burning clarifying question for which there are some natural stopping points in which you can ask. All right, so the story starts with the simple fact, you know, language data is heterogeneous, right? It's amazing that we get to work with data that's so rich in variation. It's driven by social process and intent. It's tied to the history and background of the writer. It's really reflective of the diversity of human experience. And in the literature, there have been countless studies in NLP, linguistics, sociolinguistics that study the various groups and subsets of text that constitute language diversity. You know, these works show that there are many axes by which language might vary, including community membership, time, or end applications. My own research is inspired by these studies and asks, you know, how do we make use of all this language variation, especially in massive data sets, to build more efficient and scalable language models, right? So this involves both qualitative and quantitative investigations into data sources and new modeling innovations that make use of our findings. The last few years of pre-training language models has really been embodied by this phenomenon that the performance of language models is directly tied to the amount of compute and data that we use to train it. These trends tend to follow these power law sorts of distributions where exponential increases in training data or compute yield linear improvements in performance, right? And since the original scaling laws paper in 2020, we've scaled the amount of data that we train these models onto trillions of tokens, and we're pretty much seeing consistently improving performance on a wide variety of tasks. More data, even with small models, seems to always be better. So as the models have grown in size dramatically over the last few years, you know, so is the data that they've been trained on. And nowadays, language models are trained on a wide variety of data sets, including, you know, web scrape data, code, scientific papers. Together, obviously, these data sets reflect the heterogeneity of language, but even if you look at individual data sets, you'll see a lot of really interesting variation. So let's look at one of these data sources, such as Common Crawl. Here I've embedded a single shard of about 400,000 documents of a Common Crawl snapshot with TF-IDF, and then I've clustered it with k-means, and then visualizing here with the UMAP. And you can see a number of domains that make up this, you know, random shard, including tech articles and health documents, books, social media content, many more. So the problem that I've been grappling with throughout my PhD is that despite all this heterogeneity in language, the standard recipe for training language models tend to treat all this data homogeneously. By that, I mean, instead of explicitly conditioning on this variation, to train language models, we flatten out all the clusters, we treat each sample as IID, and we train in a fashion called dense training, right, where we update all the parameters of the model with respect to all of that data. And this effectively makes all these domains implicitly discovered in the model, instead of explicitly conditioned on, assuming that we're going to fit all these domains in the training data equally well, okay? Now, this technique makes sense from a couple of perspectives, right? One, it's very convenient, right? I don't need to worry too much about my data, and modeling is as hard as it is. And two, you know, if we're trying to build systems that are broadly applicable and generalizable, training in this fashion might lead to better performance since the model has to deal with complex distribution shifts during training and thus might be robust to them during inference. But what I'd like to argue is that treating data homogeneously is the culprit of a variety of important downstream issues with language models. And I think these issues are some of the most important problems related to the safety, accessibility, and general capabilities of these systems. First, dense models tend to emphasize the largest domains in the corpus, right? So the larger the domain, the better the fit. Since the dense model is learning a single general distribution over the corpus, with standard maximum likelihood objectives, the dense model is going to perform best on the most prevalent sources of text and underperform on rarer data, right? So we showed in a paper called Whose Language Counts as High Quality that data selection practices from language model providers tend to favor the text from the most popular or viral content on the internet. So dense models are going to reproduce this bias. Second, dense training is really expensive, right? So to update all the parameters of the network, you need many GPUs active synchronously, and this expense is going to grow with the size of the network, right? So for example, Palm was trained with 6,000 TPUs, Llama was trained with 2,000 GPUs. This limits who can contribute to these systems in the first place and generally makes training and updating these models really expensive. Third, we showed in a paper called Don't Stop Pre-Training that adaptation is really important to do after dense training, but with any sort of fine-tuning of dense models, you're moving all the parameters into new subspaces, right? So with dense models, you're really susceptible to catastrophic forgetting, meaning that if you pre-train on task A and then continue training on task B, you're going to do worse on task A, right? So forgetting precludes model reuse and results in a lot of wasteful compute. And finally, dense models are really susceptible to unreliable behavior, right? So it's very common to have dense models generate toxic or otherwise unwanted content after training. We show this for a lot of models, including GPT-2 and 3 in a paper called Real Toxicity Prompts. Basically, since the dense model learns domains diffusely over its parameter space, it's impossible to remove unwanted domains from the language model after training, right? So if the dense model is exposed to hate speech or private content or copyrighted text, at some point during training, you're kind of stuck with that, right? So, in summary, dense training is really convenient. It's very impressive, but I think it increases the risks of deploying language models since it models the relationship between modeling and data, and it centralizes the language model development process by requiring a ton of synchronous compute, and it prevents cheap customization of the model and reuse of the model for downstream tasks. And I think addressing these issues are really important for the next generation of language systems. So our proposal to address these issues is to build what we call modular language models, right? So instead of training a single model in all of our data, we're instead going to train specialized components or experts, where each expert is specialized to distinct domains of the pre-training corpus, right? So we're bringing back that heterogeneity. And then we're going to imbue this ability to mix and add and remove these components as we want after training, right? So this framework is emphasizing this idea that flexibility and customization at test time is a really key mechanism to address all of these issues that I mentioned before. There's a clear relationship between model parameters and data provenance, which makes the behavior much more predictable. And users have this ability to customize the language model with very cheap operations, interacting with only a subset of experts at a time. Looking forward, I think modular models may lead to a future where instead of merely training and deploying large, dense language models, language model providers could own and distribute the development and maintenance of experts, right? So the modularity of the system should enable experts to be trained and contribute to asynchronously. Users can download the subsets of experts that are exposed to data related to their use case or just opt out as they want. And finally, compute and data could be pulled across different model designers towards experts that are part of this larger system, right? So I think this framework represents a real promise for the next generation of language models that are more reliable and decentralized. So this talk is going to describe our steps towards building modular models. We'll talk about how we introduce modularity into a language model, which, as I mentioned, should enable stakeholders to rapidly customize a language model after training. We'll also discuss our efforts to introduce asynchronous training, or this ability to train and update experts completely independently, which is important for scaling these models into massive data sets. And then we'll focus our efforts onto sparse inference, right? So despite training many parameters, users only have to interact with a few experts at a time. Okay. This talk is divided into two parts. The first part is centered around an algorithm we use to train modular language models, which we call branch train merge. And then I'll discuss our recent work around cluster branch train merge, which we use to scale modular models into massive arbitrary data sets. Okay. So let's start with the first part. Any clarifying questions before I move on? All right. All right, so let's look back at one of the main limitations of dense training, right? That it's really expensive. As I mentioned before, the main culprit of this cost is the need for synchronous compute, right? Since we have to communicate gradients and activations across all GPUs in each step, and this cost is going to grow with the size of the model, which is going to centralize the language model development process. There are lots of practical limitations of requiring synchronous compute to train models, other than the fact that it centralizes the process. Training large language models is really complex. So if a single node fails, that's going to down the entire system, and you need to restart from a previous checkpoint, which is really expensive. It's also difficult to allocate massive synchronous jobs on high-performance GPU clusters. We did some allocation of wait times on the FAIR cluster at Meta, and displayed that there's almost a linear increase in the average wait time as you allocate jobs with more nodes. And finally, there's a lot of communication that happens behind the scenes to make these systems work, which includes expensive Ethernet connections between GPUs. An alternative to dense training is conditional computation, or sparse training, right? So this is going to serve as a basis of our solution to these problems, and I might use these terms independently. In dense training, as I mentioned before, we use every parameter on every training example. Right? So this is usually implemented through some form of data parallelism or model parallelism. On the other hand, sparse training, or conditional compute, uses a small subset of each model on each example. Right? So this technique has primarily been used to scale model parameters at a vastly reduced flop count. Okay. Conditional compute has been around for a long time. I think it was first proposed by Jeff Hinton and co. in the early 90s, but the ideas are much older than that. The framework gained some new steam from a 2017 paper from Google that used conditional compute to efficiently scale a recurrent neural network language model. And nowadays, conditional compute has materialized this mixture of experts where we specialize different parts of the transformer to different data, usually at the token level, and then we merge the expert outputs. Okay, and there's lots of research on how to do this routing between data and experts properly. The two most popular approaches being learned routing, which you might be familiar with G-shard or switch, or deterministic routing, where tokens are statically routed to experts based on some feature of data. In the literature, inducing conditional computation in the transformer language model has usually focused on the feed-forward layers, right? So this is not only because the feed-forward layers tend to be the workhorse of the transformer in terms of featurizing the input. Feed-forward layers are scaled the most as we increase the overall size of the language model. You can see here in this graph of OPT models that the feed-forward layers consume the vast majority of the total flop count as the model size increases. Historically, conditional compute is focused on whether we can make those feed-forward layers sparse so we can increase the parameter count without the associated flops. But the key thing to understand with current formulations of mixture of expert models is that they still need synchronous compute, right? So these they're these shared layers like self-attention layers and embedding layers that are not expertified that need to be synchronized across all GPUs. And then there are these token level routing mechanisms that incur really expensive all-to-all communications across GPUs. And this is basically communication costs between experts that are specialized to different tokens in the same sequence that need to communicate their activations and gradients with one another. And this can really slow down training, okay? And generally, the cost of training MWE models measured in GPU hours is very much higher than dense models, and this tends to be hidden by pure flop comparisons, okay? So returning to our own research questions, we've been really interested to use conditional compute not only towards scaling model size, but also towards building modular models that we can train asynchronously, right? And so the way that we do this is by focusing on this routing problem. And as I mentioned, MWE models have generally focused on routing data to experts via learned token level gating. And so to enable this new application of conditional compute, we're going to sort of change this routing mechanism. And the insight that we leverage here is that language variation provides a really natural routing of data to experts that's going to enable this mechanism of asynchronous training. And inspired by this insight, our first attempt at this new application of conditional compute was through a method we call demix layers. And basically the idea here is instead of routing different tokens to experts, in demix, we route sequences to feed-forward experts, right, where the sequences are organized by some notion of provenance, for example, medical papers or Reddit documents, and we use conditional compute to train these experts, okay? The key thing that the demix gave us was this first evidence that domain specialization in experts yielded modular models by design, because we could basically combine and add and remove experts at any time to customize model behavior towards new distributions. And this emerged because we only needed the experts relevant to a particular test distribution due to specialization. And this sort of inspired the main algorithms that I'll be discussing today. Okay, So thinking about where we go from DMIX, it's really fruitful to think about how these models are trained in hardware land. Now consider this basic diagram of a GPU cluster, which consists of multiple cluster nodes and multiple GPUs in each cluster. In dense training, we copy each model parameter onto every GPU. Okay, then we train by shuffling all of our data, supplying mini batches to each GPU, and then computing an average gradient across all mini batches, updating all model parameters with respect to this average gradient. I'm not considering, model sharding techniques like FSDP here, but the basic outcome is still the same, right? All your weights are synchronized. So in the end, you have a single set of parameters that's been exposed to all of the data you've been seeing on all of your GPUs. Okay. In classic MOE training, we specialize those feed-forward layers, right? But this is done by feeding certain tokens to each feed-forward expert. And there are still shared parameters, right? We still have those self-attention layers, which means we have synchronization. And we have these expensive all-to-all communications, as I mentioned before. Okay, and this can really slow down training. In DMIX training, we assign each GPU a particular domain in our data set, right? And we're computing a gradient for these feed-forward layers only with respect to data from each domain, right? So this means we specialize those feed-forward layers to domains rather than tokens. And we're training many more parameters in the dense model, but actually with lower latency training because we're not synchronizing these parameters. We don't have those all-to-all communications, all right? So we've removed those all-to-all communications between experts by training in this fashion, but we still have these shared parameters, right? We still have those self-attention layers, those embedding layers, which means we still have to have synchronous compute to train this sort of expert system. And so a key question we have to motivate our next part is, can we remove expert synchronization entirely? Okay, so to train modular models without the need for synchronous compute, we propose a way to do embarrassingly parallel training, right? So in the setting, we make all parameters domain specific, which means you can completely disentangle the experts, train them asynchronously, and none of them are dependent on one another, right? So if one of the node goes down, all the other nodes can stay online, and you only need to restart a subset of the parameters, okay? So embarrassingly parallel training results in a collection of expert language models, or ELMs, which we call an ELM forest. There's lots of tree imagery, each of which is a complete language model, right? So there's no shared parameters between the experts, which allow you to train them completely independently. But there are stronger modularity guarantees over DMIX because there are no shared parameters. Right? But I'll talk about how the strength of these guarantees depends on your curriculum of training ELMs. Okay. But before we talk about how we actually train these ELMs, I first wanted to talk about inference, right? Which is a really important aspect of this framework. So how do you use these ELM forests at inference time? Okay. The naive way to use these ELM forests is just to use the single expert that you've trained, right? So if you have medical data, just use the medical expert. This assumes that the test domain is singular and revealed, which isn't optimal, right? We actually found that this naive inference technique is very rigid. It leads to poor performance, especially in out-of-domain settings where you don't really know what the domain is that you're evaluating in. So we find that relaxing this assumption at inference time leads to really large performance improvements. Basically, to increase the variance of our model, we ensemble the outputs of experts on the target domain by figuring out which domain the test data assigns to while we're ensembling. Okay, so to mix experts, we take some evaluation data, for example, this COVID-19 paper excerpt, we feed it to all the experts that we have access to, and we estimate what we call a domain posterior on the current context. This is basically a probability distribution over the experts, where higher probability for the expert means that this expert has more affinity to this target text. And then we ensemble the outputs of experts using this probability distribution as weights. So this is basically a parameter-free mixture of experts model where the routing is performed at inference time rather than learned during training, as is common with previous mixture of expert systems. And more formally, we decompose the probability of the next token, this classic language model probability, with a mixture of experts where we introduce this new domain variable D. And this is our sort of domain posterior, right, where we're trying to predict the probability of D given the history. And this is going to serve as our ensemble weights. Okay, and so to estimate these ensemble weights for this domain posterior, we're simply just going to use Bayes' rule, right? So this basically means we're going to be tracking the running likelihoods of experts on the history, which measures the affinity of each expert on the history. Then we're going to weight this by some prior that we have in the domain, and then we're going to normalize. Okay, so This way of ensembling assumes that you have to do forward passes on all the experts for inference. All right, so this is a limitation that we're going to address actually in the next part. But the prior is basically the most important part of this equation. All right, so how do we set this? We did a lot of research on how to set this prior. First, we set a uniform prior over all the domains, which we found does really poorly since it upweights certain domains that are irrelevant to the current context. We've also tried an updating prior, where we update the priors based on domain posteriors we've computed on previous sequences during inference. And this is more Bayesian, it does much better than uniform. But actually, the best way we found to set this prior is to assume that you have some extra held out data from your evaluation domain, estimate a domain posterior on that with an updating prior, and then fix that prior as for your test evaluation. This has the limitation of needing extra data, but it's reasonable to assume for most test settings, you'll have some extra data lying around to estimate this prior. But in the next part of this talk, we'll remove this requirement for extra data altogether. Okay. We also introduce a new way to combine experts by collapsing the parameters with a weighted average, where the weights are identified using the Bayes rule inference technique that I mentioned before. We'll talk a little bit more about how these inference mechanisms compare in a bit, but the key thing to realize here is that averaging allows us to have the same inference costs as a single expert. Okay. All right. So now that we've gone through inference, you might be thinking, what you're doing here is actually really simple, right? Let's just train K language models on different data sets from scratch, right? That's pretty much embarrassingly parallel, right? Well, the surprising thing is that this doesn't work because we don't only just want K different language models on different data sets. We want to be able to combine them in interesting ways, right? And so what we find is that this naive way of training language models doesn't let you combine them after training. And so to enable these exciting inference time mechanisms, we introduced this new way of learning in Elm Forest through the simple algorithm we call branch train merge. Okay. So branch train merge is basically 4 steps. First, you have to train what we call a seed language model, right? This is basically a language model that's trained on some shared corpus. And this is basically the root of all of our domain experts. And it provides some initialization of the Elm Forest when you don't have any existing elms. I don't have a lot of time to dig into seed training, but it's a really cool aspect of this framework. And there are a few things to note about here. Seed training is really critical to be able to ensemble and average elms. It has a lot of connections with theories around learning trajectories of models from shared initializations, the stability of loss surfaces. We also find that heterogeneous data makes for the best seed corpus if you really care about downstream performance of your Elm Forest. However, choosing your seed corpus properly has really strong effects on the overall modularity of the system, since the seed model is basically the root of all of your domain experts, right? So if you want to be sure that your data sets are fully contained within an expert, so you can remove an expert and be sure that the rest of the Elm Forest knows nothing about that domain, you have to be really careful about your seed. Okay. Second, we branch new experts from the seed language model or existing experts from the Elm Forest if there are any. The way that we branch experts is by taking a weighted parameter average of existing experts in the forest, where the weights are identified by some measure of similarity between the expert's domain and the new domain that you'd like to train on. Okay. And third, we do standard training of the language model with cross-entropy loss. The key thing here is that if you have multiple domains you'd like to train on, you can do these embarrassingly parallel. Okay. And finally, we merge the trained experts back into the larger collection, which we call the Elm Forest. Okay. So the key thing to understand with BTM is that it's iterative, right? So I can keep branching and training and merging as I encounter new domains in the world. And my initializations for new elms should improve as my Elm Forest grows. So I should need to do less and less training to incorporate new domains as I keep iterating through this algorithm. Okay. So how do we evaluate BTM? We have a lot of results in the paper. I'm just going to provide some noteworthy ones. But before we dig into results, it's important to understand how to actually compare dense and conditional compute models, right? So the whole point of conditional compute is that you can train a much larger model with about the same inference flops as a dense model, right? So we can't really compare models based on how many parameters were trained. We have to compare across multiple axes of comparison, right? So in this paper and the next one that I'll talk about, we chose to compare models under compute match settings, right? Either using training flops or GPU hours, We also compared models in terms of training speed, or the time it takes for each update, right? This is important to measure the effects of removing synchronization. And finally, we compare models against parameter counts at inference time, right? So why did parameter counts at inference time matter rather than training? Well, as we'll see in a bit, with models trained with BTM, you can basically modify the total size of your language model at inference time based on how many experts you want to use for a domain or task, right? And in practice, you can get away with 4 or 8 experts without substantial degradation in performance, even if you scale to hundreds of experts. So we can even match the inference parameter count of a dense model with averaging, or just using the top 1 expert. So this is the beauty of sparsity, right? So the parameter counts at inference time is a good measure of like inference latency, or how slow a model is to interact with during inference. Okay. All right. So for our evaluation setup, for this first set of experiments, we're going to use our multi-domain corpus that we curated for the DMix layers project, so we can directly compare to that method. I'll show that to you in the next slide. For the second set of experiments, we scale up the number of domains to see how BTM works with a larger corpus. And in this part of the talk, we're mostly going to look at perplexity. So lower is better, and we're going to look at different language models of different sizes, and everything is compute match between the baselines. Okay. So here's the data set we used in our first round of experiments. We divided it up sort of a large corpus into a set of domains, 8 training domains. Then we have 8 evaluation domains, which is going to test the model under challenging distribution shifts. And the way that we're going to do this is we're going to allocate some of our total budget to seed training, and then we're going to branch into these 8 domains in one iteration. Okay. So our first sort of core results show that under compute match settings, BTM consistently outperforms both DMix and dense models across all parameter scales. This is really cool, since it suggests that embarrassingly parallel training is not only more efficient, it also provides large performance improvements due to specialization of experts. And here we're using output ensembling as our inference technique. Okay. But we also find that with expert averaging, our other inference technique, it can outperform dense models at no additional inference cost, right? And this gap seems to be growing as this model size gets larger. However, BTM ensembling still does better than averaging, since the model has much more capacity at inference time. All the experts are active. Okay. Turning to training speed, we see that removing synchronization yields greater benefits as the model size grows. At our highest compute budget settings, our BTM models are about 12% faster to train than the equivalent dense model, which is awesome. It really shows that synchronization is going to slow these models down considerably. And then after getting the promising results at the smaller scale with the DMix corpus, we curated a much larger corpus of 80 domains using 64 domains as training data and 16 as evaluation data. These are pretty diverse. We've got 8 different categories of domains, and up to 20 domains each. And so to train BTM on this corpus, we basically randomly batchified the domains here, and then trained a seed language model on a subset of them, and then iterated through BTM 4 times. Okay. So amazingly, we saw that BTM or Elm Forest ensembles trained with 64 domains gets almost the same complexity as a large dense model that's trained on the same data, but for almost 3 times the amount of compute, right? So this suggests that BTM is a really effective way to scale models into massive data sets efficiently, and we'll explore this idea more in detail in the next part. One thing I wanted to mention before I move on to the next part is that if you analyze the domain posteriors on the evaluation data, we can see that the probabilities assigned to experts are really sparse. So, only a few experts are active at a time, which makes sense due to domain specialization, right? So remarkably, we find that you can basically do a top K on the domain posterior during ensembling, and you can basically get away with, 8 or 4 experts at a time without substantial loss in performance compared to using all the experts, right, at a fraction of the total parameter count. And even the Elm Forest average does much better than the dense model, right, at no additional inference costs, right? So this result is going to inspire the techniques of the next part, where we'll explore sparsity as a function of the total number of experts that we train for a fixed computational budget. Okay. So to close this section, BTM enables stronger, modular, more efficient language models than both DMix and dense training. The way that we model domains as a tree with a root starting with the seed corpus allows you to trace the ancestry of different domain experts with different guarantees based on their modularity, based on what the path is in, that this tree was exposed to, right? And crucially, I think embarrassing the parallel training could chart a path towards decentralized development of language models, where model designers could asynchronously contribute elms to a larger forest that's maintained by the language model provider. Okay. Cool. Any clarifying questions before I move on to the next part? All right. Awesome. So in this next part, I wanted to revisit a term that I glossed over so far in this talk, a domain, right? So this is one of the most important aspects of this modular framework, figuring out how to cut up the data to specialize your experts. So what is a domain? So answering this question involves defining the term domain. Domain connotes this notion of a split of a corpus. It's multidimensional, it's complex. There's probably no universal or optimal notion of domain, and it probably depends on your application or use case. In my work so far, we've taken a stance that domain is a subset of data that identifies some sort of social process that produced the data, right? So this puts humans at the center of how we organize the data, which makes sense since humans are usually generating the data that we train on. And there are social processes involved in deeming certain data as part of the same collection, right? This could be authorship, demographics, venue, politics. In the previous part of the talk, we implicitly defined a domain using this notion of provenance, right? So where does this document come from? Is it a Reddit document? Is it a biomedical paper? This is very reasonable since it's interpretable, it's easy to retrieve. And the point is that we can't get all the social context around where this data comes from purely from text features alone, right? But there's obvious limitations of using provenance metadata, right, for defining domains. First off, metadata is not always available, right? So for example, if you look at web crawl, people usually use terabytes of this data source without keeping track of metadata variables, and the URL is sometimes the only thing you have access to, and it's difficult to identify other social sort of features of a document, like authorship, from that. And so this limits the applicability of BTM. And secondly, it's really difficult to understand how BTM scales with metadata-defined domains, right? It's unknown for a fixed budget, how many metadata domains do you need? How many authors? How many subreddits? It can't be really easy to control for. So in this part of the talk, we're going to do something different, right? We're going to rid ourselves of the requirement of metadata altogether. We're going to assume that domains emerge from distributional representations of a pre-trained model, which we can identify with unsupervised clustering. Right? It has some limitations in terms of, implying that the domains are lexically driven, and it might be less interpretable based on what model you use for embedding, but it has many key benefits, right? You can now apply BTM over arbitrary data sets that you can cluster. It also allows us to have control over the number of domains for a fixed data set because we can just change the number of clusters for a fixed data set to study this property. And as I'll show you later, we use a cluster for routing, right? So there's no need for the Bayes rule inference procedure. There's no forward passes on experts, and there's no need for additional priors on the target data, right? So this brings me to cluster BTM, which is a really simple way to train a modular language model with sparse inference in embarrassingly parallel fashion. Okay, first in CBTM, we cluster the training corpus or perform what we call unsupervised domain discovery. You can basically use any embedder for the step. We use TF-IDF for scalability and simplicity. For clustering, we use a balanced version of the k-means clustering algorithm. I don't have too much time to get into it, but balancing your clusters is really important to make sure you don't get degenerate clusters. And second, we branch experts from a seed language model, just like we did before. Except this time we're going to use an off-the-shelf language model that's been trained on a bunch of data as our seed, since we know from the previous part that heterogeneous seeds are going to result in the best collection of elms. Okay, here we use OPT as our seed. And third, we do embarrassingly parallel for, embarrassingly parallel training with cross-entropy loss on the discovered clusters. And finally, merge the experts back into this larger Elm forest for future use. In this work, we're only going to consider a single round of CBTM, but I can talk about how you might do multi-round CBTM separately if you're interested. Okay. So let's look at how we do sparse inference with CBTM. First, I'll give some visual intuition before describing the inference process more formally. To do inference, we first embed the incoming test context with our pre-trained embedder. We get distances between that embedding and all of our cluster centers with our pre-trained cluster, and then we convert these distances into a probability distribution over the experts. And then we optionally take a top K of this probability distribution based on how much compute we have access to at inference time. And then we perform an output ensemble with the experts in the same way that we did for BTM using this probability distribution as weights. Okay. So more formally, here's that language model decomposition again, introducing that domain variable D, whose posterior we want to estimate for the ensemble weights. Here, instead of doing Bayes' rule, we're simply going to compute the Euclidean distance between the embedded context and our cluster centers. We're going to sharpen or smooth these distances with the temperature term. We're going to negate these distances, feed it to a softmax, and then we're going to perform a top K over that to sparsify. Okay. So this technique is improving over our Bayesian way of ensembling by avoiding the need to do any forward passes on the experts, right? The ensemble weight estimation only relies on the cluster. There's no additional data needed for inference, since we basically use the cluster for everything. And there's no assumption needed that the evaluation data comes from the same domain, right? There's a unique ensemble for every context, and there's no prior involved in our ensemble. Okay. So let's evaluate CBTM. Just like in the first part, I'll provide a bird's eye view of the most important results of the work. First, a natural question to ask is, does it hurt to not use metadata when we're specializing experts? The basic answer is no. We trained CBTM on 8 random data sets from the pile. Compared to training on BTM, we found that you can basically get pretty similar performance. In fact, I think CBTM might do a little bit better, and this might be due to the fact that it finds a different segmentation of the training data from provenance metadata. You can see here in this heat map, which basically aligns clusters to metadata across all the 8 data sets that we train on. Some data sets get assigned to single clusters. Other data sets are distributed across multiple clusters, which may suggest that metadata may not provide the most optimal segmentation. But given that CBTM seems to do pretty well, we were interested to see how it scales into large data sets. So we trained on 2 big corpora, the C4 data set and the Stork corpus. For each data set, we train on up to 168 billion tokens of text with up to 128 clusters and up to 1,024 GPUs to carefully understand the scaling behavior of BTM, controlling for computational budget and the number of experts for a fixed data set size. As with previous works, we're going to consider, language model perplexity on how that data. And in this work, we also do some few-shot text classification sort of experiments. And our basic research questions are as follows. What's the effect of increasing the number of experts for a fixed data set size? Is there such thing as optimal number of experts for a computational budget? And how does sparsifying sort of work with scale? And I'm only going to show you results from C4 because of the time constraints, but you can check out the results on Stork. They're pretty consistent, which is really cool. All right, so here's a visualization of one of our core results. Basically, each line in this plot compares the performance of models trained with different numbers of clusters and the same amount of training data. So from 1.3 billion tokens all the way down to 168 billion tokens at the bottom. So all points on the same line are compute match settings. Okay. So the first thing to note is that we train from 128 clusters, right? But note that the one cluster model is the dense model, right? So our technique is generalizing between dense and specialized models. Okay. So the first thing to note is that if you start from the leftmost point, which is in effect training one cluster dense models, you can see that we almost always get better performance by increasing the number of clusters that we train with, especially as we increase the size of the trained data set, right? So this suggests that, as we saw previously, that training dense models is worse than training expert models. And the second thing to see is that, there is such a thing as an optimal cluster count, right? And this optimal cluster count is growing as the size of the training data grows, right? So for less than 3 billion tokens, 2 clusters is optimal. Then 4 clusters becomes optimal, 8 clusters is optimal for a wide range, and then 16 clusters becomes optimal to 168 billion tokens. So this is pretty cool. It suggests that to make better use of more data, you want to train more experts. And because we're training these experts embarrassingly parallel, it's much more efficient to train on more data with more experts, right? However, we do find that there is such a thing as training too many experts for a given budget, right? So for example, we see degrading performance if you train with more than 16 clusters. And this makes sense, since if you cut up your data too much, then each expert is going to see too little data, right? And you start performing worse. But the cool thing is that at the largest budgets, our expert models trained with even 128 clusters is still better than the dense model, right? And training with 128 clusters on 168 billion tokens of text is way easier to do than with one cluster, since you don't have to train with as much synchronous compute. I think in this extreme setting, we use only 8 GPUs per expert. So now we turn to results around sparse inference. We find that using the top K experts works remarkably well, meaning that if you can basically retrieve the top 4 or the top 2 experts and perform basically the same as having all experts active. Even the top 1 model does even better than the 1 cluster dense model. So this suggests that if you only care about inference costs at test time, what you really want to do is train embarrassingly parallel and then sparsify rather than train a small model from scratch. Okay. And next, we look at how fast these models are trained, measured in terms of the maximum number of seconds per update. We basically show that as the compute and data grows, you want to be training more clusters for faster training. And this is naturally because you have less synchronization as you increase the number of clusters. We also compare to a classic MOE model that's sort of trained with token level gating mechanisms. And we show here that because of those expensive communication operations between experts, those training speeds are slowing down as you increase the compute. Okay. And finally, I want to show you a really cool result showcasing that training a really large CBTM model and then sparsifying it can outperform training a similarly sized large dense model from scratch. So we show this by training a 16 cluster model and then only use the top 4 experts, right? So that means that the effective inference parameter count is always 5.2 billion parameters. And then we compare that to training a 6.7 billion parameter 1 cluster dense model, right? So on this plot, on the x-axis here, we have the zettaflops used to train the checkpoint, and the y-axis is perplexity, right? So the first thing to note is that the zero-shot performance of these models is really starkly different because remember, we're starting with the OPT models as their seed, right? So the 6.7 billion parameter model is already trained with almost 2 to 3 times the total zettaflops of the smaller 1.3 billion parameter model. And if you align these curves based on how many tokens is necessary to train on to get a particular perplexity value, you see that you can train the 5.2 billion parameter model on 168 billion tokens of text and match the perplexity of the 6.7 billion parameter model with less than 30% of the total training flops, right? So this is pretty crazy. I think it suggests that sort of aligned with the philosophy of like the chinchilla scaling laws, that with CBTM, you could train many small models for much longer and get similar language modeling performance as a larger dense model that's trained with far more compute. So I think this result is going to inspire a lot of our future work in seeing whether many small expert models trained on the massive amounts of text can outperform a bigger dense model. Okay. I just want to flash this sort of result. We replicated this sort of experiment with few-shot text classification experiments showing that the downstream performance tracks pretty well with perplexity-based results. You can check out the paper for more information about this. And so just to wrap up here, we've shown that CBTM generalizes BTM to arbitrary data sets with unsupervised clustering. Our general results suggest that what you want to do is scale data and experts together to get the best performance and efficiency out of this technique. And I think the winning recipe is basically to train large models embarrassingly parallel and then sparsify. And I think we have early indications that this can really substantially outperform large dense models at substantially more efficient sort of compute efficiency. So we hope we can explore this direction further in future work. Okay. So I know I'm running a little bit over time, so I just want to close with a few points of conclusion in future work. So I think in summary, the modular techniques I presented today have a number of benefits over dense training. We can substantially reduce the communication overheads related to this technique. We can improve the resiliency of distributed training. We can even train on idle and ephemeral compute resources, as we did in this work, which is really cool. We've also been able to really simplify the training of sparse models compared to classic MOE architectures. We're routing sequences instead of tokens. There's no need to balance expert utilization or have additional sort of hacks to make this sort of thing work. There's no all-to-all communications. There's natural expert specialization to domains by design. And I think that, taken together, our explorations into building modular models suggest that, being more careful about our data, conditioning on language variation, moving away from treating data homogeneously, is not just desirable from a responsibility perspective. I think it also leads to more reliable behavior. It leads to more efficient scaling. It can lead to a lot of really new sort of customization options after training. And the key takeaway is that you can get all this this sort of features with better performance. So that's really awesome. And each of these techniques that I talked about today can contribute to this possible future of modular training. Embarrassingly parallel training can allow for this asynchronous development of expert models. Modularity and sparsity can allow for users to interact with experts sort of as they need for their use case. And we've sort of proposed new ways of merging and ensembling techniques for this sort of collaborative computation. And in terms of future work, I'm excited for lots of different directions that we can talk about one-on-one. Scaling to token counts that we can't really feasibly train on densely is something that I think is going to be a key part of this framework. Scaling multimodally and multilingually, relaxing assumptions that we make on the architectures of experts in terms of their tokenizers or their size. New research on training curriculums to get the best performance of these sorts of models on sort of heterogeneous and specific data sets. The analysis of emergent behaviors, I think, is a really important aspect of this framework. Do we get the sort of emergence that we see with dense models, with these sorts of sparse models? New ways to, one sort of aspect of this that might be important is to research new ways to decode and combine elms during inference. And then, another aspect of this that I think could be important is combining elms with instruction tuning, which we can talk about. And finally, I just wanted to mention some ongoing work on new styles of modularity, which I'm really excited about. I think modular language models can fall in this sort of spectrum where on one end you have dense models, right, where all the parameters are updated with respect to all the data. Somewhere in the middle you have sparse models, right, where instead of updating all the parameters with respect to all the data, you update each parameter with respect to certain domains. But taken to the extreme, you could imagine experts that are specialized to individual documents, right? And this starts to look a lot like non-parametric models, where you incorporate data stores, right, in a language model. And the way that we've been thinking about this with respect to modularity is that you can store certain domains in the data store that you don't actually want to train on, right, but you only want to query during inference time. Why would you want to do this? Well, maybe there's some data that's private or is copyrighted that you don't actually want to train your model on due to legal concerns, but you want to use that inference time to improve generalization. So along these lines, last month we released this new language model we called Silo. And this method is focused on mitigating the copyright risks of language models, but it can be extended to any sort of risky text you don't want to train parameters on. Silo first consists of training a language model on what we call low-risk text, or data that's really permissibly licensed. And then we freeze that model and add what we call a data store that contains like copyrighted information. And so we're modularizing the model with respect to risk level rather than other sorts of language variation. You can check out the paper to learn more about these ideas. We basically find that you have lots of really new capabilities that you can enable here, including training on using high-risk data without training on it, creating opt-out features for data owners, attributing predictions. And so I'm happy to talk about any of these possible directions during one-on-ones. And with that, I just wanted to give a shout out to all of my collaborators who made the work that I discussed today possible. In particular, I'd like to thank Margaret Lee, who I co-led the projects I discussed today with, as well as my advisors, Luke and Noah, and my mentor at FAIR, Mike Lewis, who provided all the critical support and advice to make all these works a reality. And yeah, thank you so much for listening, and happy to take any questions.
This is great.
Thanks.
Thanks for a great talk.
Yeah, thanks, Sachin. That was great. We have plenty of time for questions.
Yeah. I just want to dive in. I didn't raise my hand. I'm just kind of going for it. So I would love to hear a bit more about sort of your vision for the future on taking this idea of modularity to the extreme. Like I could totally imagine if we had better understanding of the contents of our data sets around the topics that are discussed, the dialects that are used, the information about the speakers or the authors, that we could push this idea of modularity pretty far. And that seems like a really great opportunity, right? But some of your work showed that at least when trying to build a large general purpose model, there's sort of a balance here. As you scale up, you want to scale up with a certain proportion of experts. So I'd be curious to hear more. My intuition is that I think better understanding of our data could lead to more experts, but I don't know. What are your intuitions here?
Yeah, I think there's obviously a balance, and it's sort of dependent on I think it's really dependent on the application, because there is a trade-off between modularity and I guess compactness of the model, right? For example, we find that if you train lots of expert models, you have a lot more specialization to specific domains, but you do incur some inference costs in terms of being able to swap in the right experts at the right time, which you don't really have with dense models. But you do have this sort of modularity guarantee, right? Where you can be more sure that this specific expert has seen this particular data set. And if you remove it, then the models, the rest of the Elm forest, doesn't know about that particular domain. So I think there's a balance that needs to be struck in terms of how many experts do you have in the system, and kind of how general you want your technique to be. There's sort of intermediate points here that we haven't really explored yet. For example, including a generalist expert, right? An expert that's just seen all the data, or maybe including the dense or the seed model as a particular expert that can probably improve generalization when you want it. And so that might sort of change the scaling sort of patterns here. So yeah, I don't know. I would say that it's really just dependent on what the needs of the application are at inference, and how many experts you want to use.
That makes sense. And I guess maybe, so the one thing that you talked about here was the sort of iterative process of branch, train, merge. You have many experts, and then you can merge them back into a seed. Maybe, do you think that if you did that a few times, then you could get some even further specialized, but yet still generally capable models? Or do you think that would maybe you still are susceptible to over specialization and sacrificing some of that?
Yeah, I think there is a trade-off in terms of specialization and general behavior. One thing we found that we're working on sort of a multilingual version of BTM right now, and one thing we have found is that if you do multiple rounds of BTM across different sort of hierarchies of language families and stuff, then you actually get way better specialization of those experts to the language that are kind of in the leaf of this tree of languages. But they are they don't do very well on other languages, even within the same language family. So I think the sort of hierarchical training is, and doing multiple rounds of BTM is really useful for specializing, but you probably want to keep around the experts that are trained on maybe multiple languages or multiple domains for the cases where you want to generalize better than maybe specialize.
Great, thanks.
Yeah.
Ian, go ahead.
Hi, yeah, fantastic talk. Thank you so much. I'm curious, so if some of the original motivation for this is the idea that if we're doing this dense training, performance might sort of be dominated by the most represented domains. So I'm curious if empirically, do you actually see some of the allocation of the improvements going to less prevalent domains, or where the performances are allocated?
Yeah, totally. That's a really great question. So in all of the works that I discussed, like we made this assumption that we're always going to balance the number of tokens that each expert sees. And this is sort of like this is a little bit contrived, right? Because like there may be cases where you don't actually want to do that. But in our setting, like we're always making sure that all the experts see the same amount of data. And so that necessarily means that, you know, the experts that are specialized to like the larger domains are going to see less of the larger domains, and you know the experts that are in the specialized the tail of the distribution are going to, you know, see much more of that the tail. And we do see like that the largest benefits of this approach are in the tail of that distribution, where you just are able to allocate more compute to seeing the tail, and thus you just do better on it. Now, this also generalizes to the clustering approach, where we kind of balance out the clusters. And yeah, I think this is probably this is where you're going to see the biggest benefits, and there might be like a cost to this in terms of like improving performance on the largest domains of your corpus. But I think like, yeah, it sort of comes back to this idea of, you know, better curriculums. So like, for example, if you combined training of like the seed language model, or combine inference between the seed language model and one of your specialized models, you might be able to like recover the performance of you know, just seeing a dense model for the same amount, or just training a dense model for the same amount of compute as those individual models. But yeah, those are really interesting areas of future work.
Thanks. Yeah. I guess I'd be curious to see how much of it is just the balancing of the data, and then like if removing possible like negative transfer between different domains actually makes it, like if the domains that are being undersampled still like improve faster because they're not experiencing negative transfer from something.
Yeah. So one other thing that we found is that a lot of the domains that tend to be in the tail are very specific language. So yeah, like you can actually those models tend to converge much faster actually. And so there could be some interesting kind of techniques there of like maybe what you want to do is like you know, allocate different amounts of compute to the tail versus like the head of the distribution, maybe in terms of like the size of the model or whatever you're doing. And maybe that's a way more efficient way to train on this like long tail. Like one limiting assumption that we make here is that all of our experts are the same size. And I think there's a lot of really interesting work to relax that assumption.
Okay, we might have time for one last quick question if someone has one. Okay, if not, I have more questions, but they're longer, so I'll save them for a one-on-one. Let's thank the speaker again for the great talk.
Thanks, everyone.